Hello students, today in this class we are going to complete the remaining applications of the Gauss theorem, and after that we'll go for problems in this class. For mains and advanced level problems also we'll do, and look at the concept of last application, okay, and some more small important points we are going to discuss in Gauss theory. So first one, okay, already we completed in the previous one. Today the first one is charges sheet we are going to discuss. There are two types of sheets we have: thin sheet and thick sheet. What is the meaning of thin sheet? The thickness is very small. So now we given the charges onto this one. You can see the diagram. So the plate, this is one of the charged plate. I can say that is a thin plate. The thickness is very small. So that is lies in the plane of x and y. It is lies in the plane of x and y. Now, so if you see the face of that sheet, the face of the sheet means this is the area. The area of the sheet will be along z axis. You can see like this, right? Now here the charge sheet you can see like this as you're looking here. Due to these charges, there is electric field. Okay, due to this charge, both the sides. Here, if you observe this one, due to thin, what is happens here? There is a charge. Now, due to this charge, there is electric field this side also. There is electric field this side also. Both the sides there is electric field. That's why you can see here there exists electric field both the sides. In the diagram very clearly given. This is side 1, side 2. Both the sides we have electric field. And here a small area, through the small area there is a, okay, I can say as normal vector, that is nothing but I can write as n cap vector. This also I can take it as n cap vector here. So now we are calculating the what is the electric field intensity at a distance, okay, from that due to this thin sheet. Formula we are going to derive here. To derive this one, first what you have to do, this is infinite charge sheet, so we can't do it directly. So using Gauss law, okay, you can do it that one. If you want to use the Gauss law, first what is the condition, at what point you want to calculate the electric field intensity? At that point we must consider one of the imaginary Gaussian surface. Yes or no? So that's why what I'm doing is, here I am considering one of the charge here. This is the one of the charge, you can say this is positive charge. Now this positive charge produces the electric field both the sides. That means below the sheet, above the sheet, because that is a thin sheet. That's why now here, if you want to calculate the electric field intensity at this point, this is the point I chosen here. The point of the distance is somewhere r distance. At this point I want to calculate the electric field intensity, suppose. Now the same distance I am taking below also, because we can also able to calculate the electric field intensity below also. Now if you want to calculate the electric field intensity, and due to this one, first you have to imagine a Gaussian surface, because this is a sheet, right, having area. So it is very difficult to find the the Gaussian surface using this one. For that, what we are doing is we are dividing this into small regions, areas like this. The number of small regions which you are taking on the sheet will give say complete area of this sheet. So it is same like if you are see the trucks which are carrying pipes. So if you see the back side of the pipes truck, okay, so the total square of the frame of the truck will be covered by small pipes. If you remove one pipe outwards, how it look? In the same way here, using the concept of that one, we are going to calculate that pipe construction is nothing but one of the Gaussian surface, I can say, because at what point you want to calculate the electric field intensity, that point we must construct a Gaussian surface. That means the point must be on the Gaussian surface. It is the point, right? So for that, what I'm doing is I'm taking the Gaussian surface here. This is the Gaussian surface. Now I'm taking the pipe structure here, both the sides. If you come across in the case of Gaussian surface, in this case, the point must be at the center of the pipe structure. So here also I can take the structure of the diagram. So you take the point little bit above. That's why we are getting the problem. So I'm taking the point here. This is a point P, right? So both the sides we taken. That means this positive charge which is there, take one, and this is producing the electric field both the sides. And now you can see this is the area vector. That area vector is acting upward direction. This is the direction of the normal vector, and this is the direction of the electric field. That means in this case the area vector and electric field both are in the same direction as they're looking like this. Now here also, below also, if you see this one at this point, I can see this is the direction of the normal vector, and that is only the direction of the electric field. In the diagram you can see this is the direction of the electric field which is given, and this is the direction of the area. So both are in the same direction. Now if you come across a case of okay, surface areas, the pipe structure which you taken, that is called Gaussian surface, contain three surface areas. First one, this is the first surface area, this is second surface area, third one is curvature, which is closed one, that is S3, third surface area. Like pen if you taken, so the front one is S1, back one is S2, and the curvature is third surface area. So it contains total three okay, surface areas. So I can write net flux enclosed in this closed surface area is equal to phi1 plus phi2 plus phi3. Flux enclosed in the first region, second region, third region. Now what is the flux enclosed in the first region? If you come across a case of flux enclosed in the first region is equal to, according to the concept of this, there is a flux takes place when there is electric field across the area in the direction of the normal. That means the electric field is E, the area vector is, you can take it as S1. So in this case, the area vector S1 which is there, okay, in terms of normal vector I can write, that is in terms of vector if you taken. Now this is the direction of this. So both are in the same direction. Same direction means angle is 0. Angle 0 means, that means there is a flux is equal to E into S1. We have a electric field in that direction. Now if you come across a case of flux 2, second region, this is the second surface area. Through this surface area also, electric field and normal vector both are in the same direction. I can write as E into S2. There is electric field. But if you come across the case of third one, third surface area is a curved surface area. In the case of curved surface area, what I am going to do is, I am taking the surface like this. This is the charge, if you say, this is the surface area I am taking for that third one. That is ds you can take, or S3 also you can take. ds3 I can take. So here electric field, how the electric field will be there? The electric field, the charges are like this, yes or no? The charges are like this. The pipe is like this. So whatever the surface area you are taking, these electric lines are passes through the surface area like this. The area vector of this one will be like this. This is the normal vector, area vector. The area vector is like this, electric field is upwards, and both are perpendicular. Perpendicular means what is the flux enclosed in this area? The flux will be 0. So the flux across this blue area in this area is equal to phi3 is equal to what I can write? That is equal to 0 simply. So there is no flux existing there. So the total flux, what I can write? The total flux, net flux equal to nothing but there is a flux due to first region, second region. Okay, that means both surface areas are, both areas are same here. That's why we can write as, okay, the flux, that is we can write as directly 2 phi. So whenever you taken the 2 phi, that is 2 into what is phi? That is flux. Flux equal to what is the formula? E into S. I can write as, because here we are taking the concept of S1 is equal to S2 is equal to S, same area above and below, because we taken the same, okay, Gaussian surface pipe. That's why both upper, okay, area, below area both are same. I can take it as S, so I can write as E into S. And due to also single charge, same charge producing the electric field both the sides. So 2 into ES I can write. So according to this one, okay, if you want to write net flux equal to 2 times of ES I can write. That is equal to, according to the concept of which one? Gauss theorem, what we can say, that is nothing but 1 by epsilon naught times the total charge enclosed in that. That is 1 by epsilon naught Q is the formula for this. Now what is the required of electric field? Electric field E into S equal to, that means E is equal to what I can write? 1 by 2S, okay, into epsilon naught into Q we can write. So what is the surface area here? The surface area of that, okay, the small region you take. In this case, whatever we are writing here, what is Q by S? What is Q by S? Q by S is nothing but called as surface charge density. What do you call? Surface, because this is the one of the plate where the charges are distributed aerially. So there is a aerial charge distribution. So Q by S is called as aerial charge distribution, I can write as that is sigma by 2 epsilon. So whenever you take on the thin sheet, the electric field due to thin sheet at any point of distance is sigma by 2 epsilon naught. In this case, we are not finding any distance of that point which is chosen from the charged plate. Okay, from this charge, I did not take any distance. I did not take any distance. That means here E is independent of. E is not proportional to distance here. It is not related to distance of the point. That is independent of distance. Simply I can say so. Electric field intensity due to this thin sheet is equal to what the formula? Sigma by 2 epsilon naught is a formula for this. Now, if you want to observe very clearly the Gaussian's pipe surface, so we can able to take any color of this, so that the color gives a very clear picture of that what way the pipe is constructed. This way the pipe can be there, and in the place of this here we have a positive charge will be there. So here we have a positive charge. Due to this positive charge, both the sides we have electric field intensity here. This is the way you can understand. We'll go for next one, that is thick sheet. Now we'll discuss the electric field intensity due to thick sheet. Thin sheet is over. Now what is thick sheet? I taken here one of the thick sheet, and microscopical, if you observe that thick sheet means it is having which a certain thickness. T is the thickness of this one. So it is having two sides, front side and back side. Both are having charges because it is one of the charged sheet. So the charges are distributed here also, same like previous, that is aerial charge distribution, that is sigma based. The total charge of this charged body is equal to Q, if you say, as you're looking like this. Now I want to calculate the electric field intensity due to this charged sheet of thick one at any point. Suppose if I want to calculate here at this point, if you want to calculate, so what is the concept? At that point P, you have to construct a Gaussian surface. So here, if you see, look at the diagram, already we taken the diagram here. This is the diagram which is looking like pipe construction. So that means the total, this sheet can be divided into number of small pipe regions as you are looking like this. So this complete pipe region covers the total area of that sheet. Now if you take on the charges here, these charges will produce the side, the left side charges will produce the electric field left side, right side charges will produce the electric field right side. So these charges are different. Previously the singular charge, both the sides it creates the electric field, but in this case the charge which is on the right side is electric field is 1, and the charge left side is electric field is different. That means there is no electric field contribution of this right side charge towards the left side, and there is no electric field contribution of left side charge towards the right side. In between, inside, there is a region inside the conductor. You know that inside the conductor electric field intensity anywhere is equal to 0. Electric field intensity anywhere inside the any thick sheet is equal to always 0. According to that one, now if you want to calculate at P point which one electric field intensity, and here imagine a Gaussian surface, that is pipeline construction. I taken here. Now this pipeline contains the charge, that is one of the charges there. Due to this we have electric field at that point. Which point? At P point. So we have electric field intensity at this point. What is the direction of the electric field? This is the direction of the electric field, we can say. Now this is the direction of the electric field, that is we are writing as E. Now area, what is the area? If you say this is the cross section of this pipe, if you say, now across this cross section this becomes the area, that is only becomes normal vector of that area. So in this case I can say this is the pipe which is called as Gaussian surface. Now the Gaussian surface can be divided into two surface areas. One is, this is the blue color one, this one region. Due to this there is electric field at this point, and we have one more is that is pipe construction. Pipe means it is having curvature. The curvature also having surface area. So I can take that surface area of this construction as a looking like this. You take the part of this. Now here the area of this one will be upward direction. The area will be normal vector will be upward direction. Area vector will be upward direction. So now we have two surface areas are there. One I am calling as S1 surface area. Second one is called as S2 surface area. So due to this one we have a flux. So the flux, total flux is equal to, that is nothing but net flux equal to totally is due to two surface areas, that is phi 1 but phi 2 I can write. Now that means I can write as what is phi 1 value? that is phi1 is equal to, I can write as according to basic formula E into surface area, that is ES1. Similarly, what is flux due to second surface area, that is phi2 is equal to E into S2. Now, if you observe the flux phi1, in this case, now the electric field and area is both are in the same direction. So that means theta is equal to 0 degrees. When the theta is 0 degrees, what is the flux maximum? So there is a flux will be maximum, that is E into SI. But in the case of second region, if you observe this one, in this case, in the case of second region, the electric field through this area, it is passes like this. This is the direction of the electric field, you can say, and this is the direction of the area vector. So both are making an angle 90 degrees. Both are making an angle 90 degrees. So in this case, I can write as E into S2 is equal to nothing but perpendicular. So that means what is the flux? That is 0. Along the surface, flux is 0, and normal to the surface, flux is maximum. So in the case of first surface area, flux is maximum. In the case of second surface area, flux is minimum. So phi2 is equal to E into S2, that is 0. So if you apply this one, so net flux is equal to nothing but, okay, phi net is equal to nothing but how much you are going to get? Only phi1, that is nothing but E into S. So according to concept of E into S is equal to what I can say according to Gauss theorem. Gauss theorem states that it is equal to 1 by epsilon naught times the charge enclosed in that. This is the way we can take. Now you can write the E. E is equal to nothing but what I can write, that is 1 by epsilon naught, that is Q by S I can write. What is Q by S? Q by S is nothing but called as charge per unit surface area, nothing but aerial charge density sigma. So I can write this one as sigma by epsilon naught. So in the case of thick sheet, the electric field intensity at any point, either both the sides, that means towards the right at any point is sigma by epsilon naught, towards the right also sigma by epsilon naught. So in this case, the charges which are producing the electric field towards the right cannot be produced electric field towards the left because of due to this thickness of the sheet. That means A is equal to sigma epsilon naught. And also another point we have to remember here, this electric field intensity is independent of distance. We are not getting any distance point because I chosen the point here. The distance of the point wherever you chosen in the expression, we are not getting any distance relation. So E is independent of, that is not depends on distance of the point. So it is independent of the distance. It only depends on charge density of that one. So this is most important concept, and this concept we are using in the capacitors. Okay, so what is the flux enclosed due to thick sheet of infinite, that is equal to E is equal to sigma by epsilon naught is the expression of this one. Now up to now we completed the applications of the Gauss law as a numerical method based. Okay, Gauss law concepts is over. Now we are going to discuss about theoretical based Gauss law applications, and that questions will be asked in the competitive examinations. Just will, okay, you have to understand how to solve that, write the formula for that okay, particular charged bodies, how the electric field, how the flux will be calculated. Now we'll discuss about flux due to some okay, spherical shape bodies, and at different points we'll discuss. So here I taken two spherical bodies here, okay, hemispherical bodies. In this case, this is the center of the first and this is center of the second. Now what I'm doing is I'm taking the line here. This line is passing as we're looking like this. This is the way the line is passing. This is the center of the spherical surface, and here also I can take the line of that. This is the center of the hemispherical surface. Now what we are doing is, concept is, first I'm keeping the one charge Q here. Whenever the charge is placed at that point, now what is the flux enclosed in that surface area? Now this is one of the hemispherical surface area, that is if you see the curvature is actually like a okay surface area. Now it is exactly on the base of this hemispherical surface. Base means this is the base, and on this base we kept this charge. Whenever the charge is kept, what happens? There is electric field intensity takes place due to that charge. That electric field intensity as a line of forces, I can draw like this. This is the way the electric line of forces will passes. Just a minute. So this is the charge if you Q if you taken, then in this case this electric line of forces from this charge will passes like this. We can take many lines, as many as possible. We can take it. This is the way we can take the electric lines. Now these electric lines which are passing every point, okay, this every electric line touching the surface of this hemispherical surface once. Yes or no? So that means there is a flux will be exist due to this hemispherical surface. What is the flux formula for that one? Flux equal to basic formula E into surface area of that. So in this case, electric field into surface area of this curvature. Now it is if you taken the part of it is a part of a football, right? What is the surface area of the spherical body? That is 4 pi r square. So in this case, this is half of that one. That means I can write as 2 pi r square is the flux enclosed in that closed surface area. I can write. What is r here? Radius. You know that what is radius? How to measure? So from here to here is the radius of this hemispherical surface. So this is a way you can. Now suppose if the charge is here, it is not at the center, it is outside. In this case, how the electric lines passes in this. The electric lines, one line I can take it as like this. This is the way the electric lines passes. The case of from the base, and another lines, the remaining lines will be passes like this. This is the way the number of electric lines will be passes in this case. Now these electric lines of forces, if you observe this one, every time when they are passing through hemispherical surface, it is touching two points. This is one, this is two, and this is one, this is two, and this is one, this is two times. And it is entering here, it is leaving here. 2 times it is touching the surface of the hemispherical. So whenever the electric line of force are touching the passing through the surface areas and touching the same surface area 2 times, in that case the flux will be equal to the flux enclosed in that closed surface area is equal to always 0. So that means in this case the flux equal to E into S I convert, this value is equal to 0. We can, because already we know the concept of this one. This is called entering flux at one point. This is called leaving flux from the another point. Entering flux if we take it as positive, and leaving flux if we take it as a negative. So plus and minus will becomes 0. So total net flux across that closed surface area becomes equal to 0 according to the concept of this. Next one, if the charge is placed below at anywhere, that means here is a charge at infinite distance, you can say. In this case, the electric lines will passes through the base of this hemispherical surface. In this case, the electric lines of forces we can take it like this. So electric lines of forces, if it is at infinite distance, these electric lines of forces will be passes like this. So from this, what we can understand here, from this we can understand the concept here. So when the charge is taken at infinite distance, these lines becomes parallel, and these parallel lines which are there, they are passes first entering into this base of the hemispherical surface. Now after entering into the base of the hemispherical surface, anyway these lines are passes through the curvature also, understanding. But here we need to understand all the curved parts are not going to be passes. So that means I can say here it is entering at one point and leaving at another point, like that from the curved surface. But in the case of base, it is entering at the base and entering into the hemispherical surface. So in this case, the flux across that through this hemispherical surface is equal to E into the area of the base you have to take. That means what is the area of the base? This is the base. The base area is equal to what I can write, that is nothing but pi r square, we can write, because it is in the form of a circle. So it is like a disc like you can take. So what is the flux enclosed in the hemispherical surface is only E into pi r square. There is no flux enclosed in the curved surface area. Now for the next one, I taken one of the cone structure, that is ice cream cone like cone structure. So if the electric lines are passing through the cone structure, so what is the flux enclosed through the cone? That means this is the way the electric lines are passing. If you say the electric lines are passes like this through the cone, in this case what is the flux enclosed in this? To calculate the flux enclosed in this, phi is equal to nothing but, basing on this one, if you observe the diagram, this is the base of the cone and this is the height of the cone. This is the height of the cone, right? As per the geometry, we can say. Now, if r is the radius of the cone and h is the height of the cone, if you say, in this case, the total area of this one, according to flux, we can write E into area. But the total area is equal to, we can divide into two parts as two, okay, uh, right angle triangles, like half into area of this cone, I can write as, that is nothing but half into, that is, sorry, 2 times of total, okay, this is how many times, 2 times of half into base into height, area of this part. What is the area of this part? That is half into base. What is base? R, height is h. So 2 get cancelled, so flux equal to how much you are going to get, okay, that is E into R into h is the flux enclosed in this through one of the cone structure. Now here one more concept also we can include here. In the case of this hemispherical surface, if the charge is placed just below, the charge is placed just below, here if you are placing here, in this case, what is the flux enclosed in that? To explain this one, the electric lines will be passes as you are looking like this. The electric lines will be enters and they passes like this. So in this case, there is a passage of electric lines through the surface of the base as well as curvature. So there is a flux will be there. But these charge is outside. That's why there is a electric lines also present outside also. This is the way the electric lines will be passes outside also. That means there is no area here. That means half of the electric lines will be above, half of the electric lines will be below. That's why when the charge is at here, the flux enclosed in that is equal to, we can write as q by 2 epsilon naught, we can write, because all the electric lines are passing through the third surface of the hemispherical surface. In that case, we can write q by epsilon naught. And in terms of without area taking, if it is the charge is just below, in this case, okay, upper part of the electric lines will passes through the surface and below part of the electric lines will passes through the passes into the air. That means what is the flux enclosed in that? Q by 2 epsilon naught is the flux enclosed in that area. Like this, we need to understand the concept. Next concept, I taken one of the spherical ball. I taken one charge here near to this. That is, now what is the what is the flux enclosed in a particular region of this spherical body? Particular region means, suppose if the region is given here, what is the flux enclosed in this one? The region is given here, what is the flux enclosed in that? Like that, the question will be asked. So there is two regions I taken here, A region, B region. Now what is the flux enclosed in the A region and B region? To understand this one first, here the concept is, whenever you taken the spherical body, when the charge is taken near to this, so this is the one of the conductor. That's why what happens here, the charges will be induced on the surface of this body as they are looking like this. Now you know the concept of induction. Due to the charge, near end positive charge and opposite end will be, near end will be negative charge and opposite end will be positive charge will be accumulated. Yes or no? This is the point where you will get opposite charge. If the charge is Q is positive, then you will get here all our negative charges will be accumulated here. This is negative charges means this end you are going to get similar charges, that is like charges will be accumulated in the other end. So this is the way. Now in this case, the region A, if you observe that one, the region A will be, what type of charges it contains? Positive charges. So the flux enclosed in this is equal to due to positive charges, we can say. Now what is the flux enclosed in this another part, B part, that is due to negative charge. So there is a positive flux is there, that is at A point, and there is a negative flux is there, that is at B point. Now suppose if you taken the concept of certain part of this, if you taken certain part of this one, in this case, that certain part also we can calculate by taking the geometrical construction based on the how much angle it is making. Based on that, we can able to explain the flux through that surface area. Suppose if you want to explain this one, suppose this is the way I can take the diagram of this one. Now if you take on the line here, this is the curvature. If you want to calculate, you take geometrical straight line here. Again you take another geometrical straight line like this, touching the points of the surface, because short length if you taken without taking the curvature, that small curvature part if you neglect it. And according to that one, next if you taken the one more line here according to geometry, so we'll get one of the structure of this frame we can see here. Now in this case, how much angle it is making, if you want to understand this one, if it is the right angle triangle, if it is making, in this case if it is the right angle triangle, in this case suppose it makes an angle 60 degrees. If you say 60 degrees, it is make an angle 60 degrees. If you say this also, if it is 60 degrees suppose, then what is the total angle will becomes 120 degrees. So the flux enclosed in the 120 degrees, if you want to calculate what is the total charge of the body, that is q. So when the charge is totally q, the flux enclosed in that is equal to phi, that is across how much angle, that is 360 degrees of this. Now what is the per unit degree, that is nothing but, okay, so we can write that charge per unit degree, that is equal to flux per unit degree, we can calculate, that is nothing but we can write as 5 by 360 per unit degree flux will be present. Total charge is q, total flux is pi. That total flux is contributed in the 360 degrees of the sphere, that is 360 per degree 5 by 360. Now whatever the portion you are calculating, how much angle it is, 120 degrees. So if you calculate this one 120, how many times it will cancel? 3 times. So that we are going to get, it is 5 by 3 here. So that means what is the flux enclosed in that? The flux enclosed in that is equal to, in the total flux, 1/3 of the flux will be contributed here. The total flux of this one is equal to, if we say phi, the flux enclosed in this part is equal to phi dash is equal to, we can write as 5 by 3. This is the way you have to understand the, apply the concepts of this one. Now next concept is in the case of cube. I taken one of the cube which is 3-dimension body. So this is center of this cube. So at the center of the cube I taken a charge, that is, if the charge is placed at the center of the cube, now what is the flux enclosed through this total cube? So if you want to explain the flux enclosed in that one, so you know that electric lines, how they passes from the charge cube. So electric lines will be passes from the charge cube. Some lines passes like this, and some lines passes like this, and some lines will passes like this, and this is the way the electric lines will be passes all the directions from that. So if you observe these electric lines, now these electric lines are passing through the cube and coming outside. So in this case you need to understand, these electric lines are passing through each surface area. How many surface area the cube contains? You know that is 6 surface area. This is 1, if you say this is 2, and this is 3, and this is 4, and whatever you are seeing, the front and back end, this is 5th end, and another back end is, that is 6th one. Total 6 faces will be there for the cube. So these electric lines is passing through all the 6 faces. That means the flux across each face, this is the each face, one face if you taken, the flux across that one is equal to, if you say as phi, the total flux is equal to, net flux is equal to, how much I can write, that is 6 into phi. Okay, that means each, okay, you take it as phi dash, the flux across each face is phi dash, if you taken 6 into phi dash is the formula, because one phase, two phase, three phase, all the phases contains the flux, that is phi dash. Then total flux equal to, through the cube is equal to 6 pi dash. Now our requirement, what is this flux across each one? So according to concept, one single charge contributing the total flux. So you know that the flux across the total surface area is equal to q by epsilon naught, we can write. So in this case, the q net is nothing but total flux, that is q phi net is equal to q by epsilon naught due to complete charge, single charge. So I can write this is q by epsilon naught is equal to nothing but 6 pi dash, we can write. Now what is the flux enclosed in that small region? That is nothing but, we can write as 5 by 6, we can write, that is nothing but q by 6 epsilon naught. So the flux enclosed across each surface area is equal to, in the case of charge is placed at the center of the cube, is equal to q by 6 epsilon naught is the formula for this one. Now this charge is, we can place it at different positions. Now we will go to the next discussion of the points of that. Next, in the case of cube, if we are placed the charge at the corner of the cube, at one of the corner, now what is the flux enclosed, okay, through that surface of this cube? If you want to calculate what is the flux enclosed in this, and if you want to calculate the flux enclosed through the surface of this one, first what you have to do is, this charge is not in the closed surface area. If you want to calculate the flux using Gauss law, the charge must be within the closed surface area. So what you do is, you take the surface areas of the body. That means what is the shape of the body? Cube. So you take the similar shape of the cubes. So that similar shape of the cubes can be taken like this. This one cube I taken extra, that cube I place side of this one, and one more cube I taken here, that cube I taken above, and one more cube I taken like that. So I'm taking the 4 cubes as you're looking here, 4 cubes. These 4 cubes are after placing as you're looking here, it is covering the charge at one point, center, one end, whatever the face you're looking, it is covering. It is only 3, and like that we can go for next one, fourth one. This fourth, will be like this. So like that, how many cubes I can choose here around the charge? It's already we have 1, and topmost bottom, if you observe this one, this is 1, this is 2, and we can place one more cube that is in front of this one here. This is a third cube, I can say. This is a third cube, right? One more cube if you taken, I can place it here, that is fourth cube. So below, this is third cube, this is fourth cube. So below the charge, that means this is the charge, and the charge is surrounded by how many cubes? 1, 2, 3, 4. Similarly, in the above also we can write as 1, 2, 3, 4 cubes we can keep. Totally, how many cubes are covered? That when the charge is at the center, that is nothing but 8 cubes. That means if you taken the charge at the center of the one of the cube, then that will be covered by 8 cubes. Then what happens? This totally becomes a big cube. The big cube contains how many sides? 6 sides. That is contains totally 6 sides, and which creates that the charge will now at the center of that big cube. In this case, the total flux in that is equal to 5, if you say. So according to the concept of what we discussed, the flux across the each face, that means total 6 faces are there. This is the complete face. Now what is the flux across that face? That flux across that face is equal to pi dash, I can write. That pi dash is equal to pi by 6, I can write, because already we done in the just previous. Now that is one cube. Here 8 cubes are there. 8 cubes forming the 6 faces. The flux through the one of the face of that one is equal to pi by 6. Pi by 6. Now if you observe this one, how many parts are there in the one face? That is, I can write as 1, 2, 3, 4 parts are there. So total flux across the that means across this one is equal to each part, how much you are going to get? That is pi dash is equal to nothing but across this one, total is pi by 6. Now what is that pi value? According to how many cubes are there, it is passing through 8 cubes are passing, right? So pi dash is equal to, that means if you want to calculate the flux across each face, this is pi double dash is equal to, don't take pi dash, pi double dash you take it, is equal to how much you are going to get already? Flux by 6 into, these are how many phases? 1, 2, 3, 4. Each phase is equal to by 4. That means nothing but we can write as flux across each phase is equal to 5 by 24. You will get, that is nothing but 5 by, that means, so 5 we can write as in terms of q by 24 epsilon naught. So this is the answer for your question. The flux passing through one of the face of the cube is equal to, we can write like this. Now if you want to calculate in terms of other way also, we can write the flux passing through one of the cube of this face. Suppose if the electric lines are passing through this one, if you say like this, in this case across the complete side is equal to 24. But if you come across, if you observe this one, this charge is on the top of the one of the cube. Okay, that's why what happened, these electric lines will be passes across this one, and the remaining 3 will be, the electric lines will be passes as they're looking like this. Remaining, the electric lines will be passes as they're looking like this. First phase, second phase, and fourth phase. Electric lines will passes like this. So, and across the third, already charge is on the surface, along the surface flux is 0. So remaining 3, okay, cubes it is passing. So flux across each phase, okay, we can, triple dash is equal to, we can write as 3 times of q by 24 epsilon naught we can take. That is equal to how much you are going to get? 8 times, that is flux across each cube is equal to, we can write as q by 8 epsilon naught we can take. So according to the question, we have to take, if the charge is placed here, if the charge is placed a little bit above, the concept is changes a little bit. If the charge is exactly at the point, q by 8 epsilon naught. If the charge is a little bit above, then q by 24 epsilon naught. Like that, the small concept will be varies here.